Hello, it's Brad here, and today what I'm going to do is talk about an interesting case of something I found in the software. I don't think it would technically qualify as being a bug. However, we are putting out a notification treating it as such, just to make it clear what the software is doing, why I'm raising this issue, also why I don't think you should be too concerned or alarmed by it. But basically, I'm going to be talking about out-of-plane shear for walls. So you can see here I've got a wall. I have it entered in here. I put in my height as 3 meters, and you see it drawn over here. So that's my 3 meter span. And then I'm going to go through and I'm going to apply a 1 kPa wind pressure, or 1 kilonewton per meter, because it is all per meter length of wall. And so when I go through and design this for flexure, I'll just go through and I'm getting one number 10 bar placed at 1200, or every 6th cell. And you'll see the design works in flexure using a 15 centimeter, 15 MPa block. So that's what we're looking at. Now, when I go through and I design it for shear, you'll go and you'll see there's no issues here. We have a factored shear of 2.1 kilonewtons compared to the resistance of 6. And so we're only loaded to about a third of our resistance. But this resistance of 6 is something I want to point out as a potential blind spot here, because I think there's a little bit of a flaw in the way that we're looking at it, and we're missing a case that could possibly be more critical. And so before I get into showing a little bit more details, I just want to show we do have these two options just to review for the output. So right now we're looking at the simplified result, and we have the shear tab selected. But if we click on detailed, you'll see we actually have some more information that shows up here with formulas, with code references and everything. And so this is something I'm going to be referring to. So switching now into a picture of the diagram here, what I would like to do is talk a little bit about, let's go back here. Is look at this wall. So first of all, our shear diagram. When we're going through designing this for shear, I'm going to go through and just sort of draw it. So it's pin, so we know half our shear is going to be at the top and the bottom. Just a little bit of mechanics review. So here's our boundary conditions, and so we're going to have lateral reactions here and here. And our factored shear is actually going to be equal to our pressure times the height over 2. So what this works out to is having a factored shear, or VF, of 2.1 kilonewtons, and that's right up here at the top. And then we're going to have that same value down here, VF of 2.1 kilonewtons. Now between the two, since we have the same factored shear, I'm going to be a little bit more concerned about what we have up here, just because we have less axial load, which adds a little bit to our resistance, that PD term you might recognize in the formula. So in any case, what I really want to focus on is that we're looking at the very, very top of this wall, because that is where we have the highest shear. And you might be looking at this and thinking, you know what, I feel like that's pretty realistic to do, just because, well, if I'm checking a wall for out-of-plane shear, I'm going to be most concerned about where it's the highest, right? And so that is actually what I wanted to get in on here. One other thing quickly to point out is that you'll see a variable used here. We have an F'(m) effective. And so when we look at our actual wall, you'll see that we have a mix of grouted cells here along the length of our wall. I did mention every 6th cell is grouted. So and then we have the remaining 5/6 are hollow. So we have, let's write this out here, 1/6 grouted, and then plus we have the 5/6 hollow. And since this wall is built, so we are using a 15 MPa block, we're not actually using those values for our F'(m), just some more review. Actually, for our grouted, we have an F'(m) of 7.5 MPa. I'll put a little G there. And then for a hollow, we have an F'(m) hollow of 10 MPa. This number was actually 9.8 in the 2004 standards. So in any case, we take a weighted average looking at these different areas. And so you'll see in the software, when we look at our results, we have an F'(m) effective of 9.13 megapascals of MPa. So this is one of the main numbers that we use when we're resisting our out-of-plane shear. And so that's just why I'm pointing that out and establishing that. And actually going down here, you'll see, so over here, these are these F'(m) values that I mentioned, the 10 and the 7.5. But actually looking over here now, this is where we get into our actual shear results. And so you'll see we have our factored shear, our factored moment, and then down here we have our the main things I want to point out. So here's our shear resistance, VR, of 6. I referred to that before. We were comparing that to the 2.1. And then within there, we have this VM, or like it's basically a unit shear strength in MPa. And that's this number here that I want to get in, really dive into. So if we look at our inputs here, we have it's a factor of, we have 0.16 times 2 minus this ratio, MF over VF dV. And then we have multiplied by the square root of that F prime M effective. So if we want to go through and take a look at this number, you'll see we have a VM value here from the software of 0.64. And where this comes from, so we have VM, so we have the 0.16, and then we multiply that by 2 times that ratio, or 2 minus that ratio, so MF over VF dV, and that is all multiplied by that F prime M effective. So breaking down this ratio here, we actually know in the standards that it has to be taken as between 0.25, this whole ratio, MF over VF dV, and 1.0. So depending on our loading, we might be lower than that, in which case we take the 0.25, and if we're higher than that, we take the 1.0. And so in this case, we're pretty much at the very top of the wall. Just to review, at being at the very top, this is where we have the highest factored shear forces. But if we look at our moment diagram, I've got it shown on here, it's actually, if we look at right at the top and right at the bottom, these two locations, we actually have a factored moment of, we actually have a factored moment of 0 down here. So that being said, what the software does is it actually, just to be conservative, it looks at the moment along the height and takes a value within there. So you'll see that we're actually using a value a little bit higher than that. We have 0.1 that gets put in here. So if we go ahead and we put in, we want to figure out what this factor is. So MF over VF dV. So let's put in our numbers. So we have 0.1 kilonewton meters. We're going to divide this by our shear, which is the 2.1 kilonewtons. And we're going to multiply that by our shear depth, dV. So for an out-of-plane wall, that's equal to the depth to our steel. So in this case, we just have dV of 70 millimeters. So that's the bar being placed in the middle of the wall. And just recall that the whole thickness is 140, so this is half of that. So we have 0.07 meters in there. So if I go ahead and I plug that in, what I get is a ratio of 0.68. And so that falls within our limits that we have here. It's bigger than 0.25. It's less than 1.0. And so in this case, we go ahead and we can just use this number. So if we want to go back to VM, so we can do that shear strength, VM is equal to 0.16. Now we'll plug in our numbers, 2 minus 0.68. And you'll recall we established before our F prime effective is 9.13. I think. Let me confirm that here. Yep, 9.13. Didn't want to lead you astray. Okay, so we'll go and we'll put that into our calculator. And this is where I get a VM of 0.638 or 0.64 megapascals. And that is what you see here in the software. Okay, so far you're watching this, you haven't seen anything wrong. And that is because this was the very thing that I was looking at. You know, the software is doing exactly what it's supposed to. But one thing that I was looking at, especially when I was plotting these curves along the height of the wall, this MF over VF dV ratio hits its upper limit pretty quickly. And so what I want to do is actually look at, if we look at one course below within here. So actually, at any point we can do in the software, we can look at the loads analysis results. It'll show you the shear and the moment at different locations along the wall. And so if we go even one course below, where our moment is slightly higher, even within the simplified shear results, you can look at the results along the height of our wall here. So this is at the very top of the wall. If we look at just a little bit higher, so we have a moment of, it says 0.4, it's actually 0.38 or 3.39 on there. And so if we look at this, our shear resistance is just a little bit higher, then you'll see that our numbers change just a little bit here. Okay, so looking at this wall, so one course below. So this would be, we were at 3 meters, so this would be at 2,800 millimeters. So we have a factored moment, so MF, of 0.39 kilonewton meters. We have a factored shear now that is lower as well. I'll go back to the software quickly. You'll see, if I look here, you'll see that our shear is a little bit lower as well. We're down to that 1.82 kilonewtons. Our dV is the same. So if we go through and we punch this into our calculator, so 0.39 divided by 1.82 divided by 0.07, punch that in, we actually get this ratio, MF over VF dV, of 3.1 or 3.06. So this number is greater than 1, therefore we're just going to use 1. So when we go through and we calculate VM, what this means is that if I plug this in now, since this ratio is greater than 1.0, we have 0.162 minus this ratio, which we've taken as 1, times 9.13, the square root. So we plug this in now, we get 0.48 megapascals. So this is significant compared to the 0.64 that we had before. And if we actually go ahead and we plug this into our VR formula, so this is the equation that takes into account, uses that shear strength and everything else. So I'm going to go to the detailed shear results. So we plug this VM value into here where we got 6 before. You'll notice we actually get a shear resistance now, VR equals 4.5 kilonewtons. So comparing it before, we're no longer at the critical section. So the big changes that I want to point out here is that, so VF was reduced by, what was the difference here? So we went from 1.82, calculating this on the fly. So that difference of 0.28 between the factored shear here and at the very top, we divide that by 2.1. So this was, we're designing for a lesser shear, so it's about 13% less. It results in a much bigger drop in shear resistance. So VR reduced by 25%. So the reason I'm pointing that out is because oftentimes our shear resistance, if we look at it right at the support, or actually I'll go up here, we'll get one value. So in this case, we have a shear resistance that is way up here compared to the factored shear. I'll even sort of draw over the top of the cross section way up here. But actually, if we look one course down, it actually drops by quite a bit to the value that we get for the rest of the height. And so the same thing happens on this side. And so when we're away from those supports, basically we get a big bump by checking it right at the support, whereas the difference between this and this value here is a much smaller change. And so what we're going to do in the software is just change it to checking it along the height for diagonal shear. But in the meantime, consider yourself informed. This is basically what we're looking at. Now, I want to go back to quickly talking about why you shouldn't be too concerned, because first of all, these types of walls, when we're looking at out-of-plane masonry wall design, they tend to be governed by flexure just to begin with. And so I haven't even personally seen a scenario that one of our engineer users has sent in showing a situation where you're really being governed by the out-of-plane shear. But even so, when you go to a larger unit, just because that shear depth gets larger as well, you'll see the problem also disappear. So if I go to a 20 centimeter block, I have the same design here. I've already designed it for shear. I'm going to click on this again. If I look at my results now, or even for a 25 centimeter, you'll see this VM value that we look at is actually 0.48 MPa. And that is just because our DV gets larger, so we're taking it already. Like the way we compare these numbers, it just works out that way. So really it's for very small masonry walls. So usually that comes along with not having a lot of lateral load. Maybe it's just internal pressures or whatever else you're dealing with. And so this really, I mean, the example that I showed sort of accentuates. We have a lot of hollow masonry as well in our wall, so not a lot of grout. But it just so happens that it works out that that's how these situations play out. So as soon as you start to get even to a 20 centimeter block, your answers don't vary by too much either. And in any case, if you do have any questions about this in the software, or you're concerned about one of your designs where you think this might have come into play and affected the results, you can always feel free to contact the Canada Masonry Design Center. We are the authorized technical service provider for the MAS software, and a lot of what I do is handling these types of questions. So if you are concerned or you do have questions, please just feel free to reach out. Thank you.